is this thing made of? Which is a really fundamental question, right? We ask that of everything. We ask that of ourselves. What is our body made of? To some degree, we ask of people, sort of, what are you interested in, right? What are your views? What are you made of? But of course, we also ask it of the universe itself. What are you made of? And so that adds a really important dimension to what astronomers can provide.
Welcome to Origins with Dr. Natasha Wilson, where we explore the unique origin stories of leaders in science, technology, engineering, arts, and mathematics, also known as STEAM. Today, I will be a conversation partner with our guest, Professor Anna Frebel. Professor Frebel is the head of the Division of Astrophysics in the physics department at MIT. There, she conducts her research on the chemical composition of the oldest stars in our Milky Way Galaxy and in small dwarf galaxies nearby. She has authored more than 165 peer-reviewed journal articles in her field, including in Nature. Professor Frebel has received numerous awards and honors, such as being named an American Physical Society Fellow in 2022, being named ScienceNews Magazine's 10 Scientists to Watch in 2016, and receiving an NSF Career Award in 2013, among numerous others. Professor Frebel has also published a book called Searching for the Oldest Stars, Ancient Relics from the Early Universe through Princeton University Press. She is also an avid science communicator, engaging in lectures, interviews, and theatrical presentations. She was most recently featured on the Lex Friedman podcast and will be performing a living history presentation of Dr. Lisa Meitner. We welcome Professor Frebel to Origins and invite her to share with us the touch points of her childhood and early career, which has brought her to where she is today. Welcome, Professor Frebel, to Origins, where we like to start off in childhood, and especially just to learn a little bit more about the touch points in your childhood that led to where you are today, your career and your interests. So please tell us a bit about how you grew up.
Hello, I'm so glad to be able to speak to you today. Now, my childhood was in Germany. I'm from Germany, and I grew up as a fairly normal child. uh, I have two siblings, and we lived with my mother. And I like being outside. I climbed all the trees that were always running around in the woods. Of course, that was the time before electronics and devices, and there was occasionally some boredom. But my mom always said, well, Anna, if you're bored, you have to become creative. Why don't you go and think about something, and then we can discuss what to do. It's summer right now here, and it certainly reminds me of the times when there was no school, and I would just get so bored because my brain always needs to do something with my hands, with my body, uh, thinking about something, doing something, running around outside. And yes, the saying, oh, Mom, I'm so bored. What can I do? And her saying, well, think of something, be creative. Definitely rang true just a few days ago again. so, uh,
So, did you have any moments in your childhood that were kind of indicators of your future career in astronomy and astrophysics?
Less so in my early childhood, but starting with my teenage years, I liked to discover things, in the sense that I like to know how things work. And again, I guess perhaps stemming from my boredom, I would ask questions. And sometimes I liked the answer, sometimes I didn't. Yeah. And I certainly developed an affinity for science-based subjects in school. Because you could ask questions, and there was always an interesting answer. When you think of history, it's like you can ask questions too, but the answer has already played out, right? So
Mhm.
you can only kind of maybe learn from the mistakes of others, but there isn't so much that you can discover yourself anymore, right? It's not looking ahead, it's more looking
Mm-hmm.
past, back to the
Mm-hmm.
past. And that is an important part of life. I think it's quite healthy to look back sometimes. But I very much enjoyed asking questions and having conversations with people about, little things, big things. Uh, yeah, so I definitely was an observer, running around again, as I said, in the woods, just observing things, the world around me, and sometimes falling from the trees too. So gravity was with me from an early age.
So during school, you said that you began to have an interest in your science classes. Was it all of your science classes, or did you start to have more of a affinity for physics? So, kind of, what were your classes like? Maybe what were some of your favorite classes, and what were some of the classes that maybe weren't your favorites?
I liked most of them. I really liked math. That seemed easy and straightforward. I really liked geography and biology. I almost became a biologist.
Yeah.
I like the little things, how
Mhm.
how cells operate, what floats around in a cell, how a cell functions, how organisms are built, what they can do. I found that really fascinating. But I will also say that I had a really engaging teacher who had a really good way to convey, exactly how this all works.
Mhm.
So that had a lot to do with it. Um, earth science, I really enjoyed how, learning about all the ages and stages of how the earth sort of came about and evolved. Evolution, of course. Um, Physics wasn't at the top of my list for quite a while, but again, I think that had something to do with the teachers. um, Chemistry was a so-so for me because we had a lot of teacher shifts. And first, there was a teacher I just couldn't with at all, but then we had a really great one, and she used to be a scientist,
Mm.
and I would go after class and just have a chat with her, and she let me have a chat with her about, my questions and my things. And at that point, she also knew that I hadn't developed an interest in astronomy, and sometimes we would just talk about that. Had nothing to do with chemistry. We just had a scientific chat about some topic, and I enjoyed that very much. And so that certainly helped to uh, have me keep asking questions rather than feeling shot down. My
Mhm.
math teacher, even though I liked it, he was not so good in welcoming questions. He
Mm.
he even once told me, "Oh, Anna, you're smart enough. You don't need to practice more." When I asked for practice questions, and I was like, "Is that really how you would want to encourage
Mm.
students?" And I didn't
Yeah.
actually feel like I could do it all, and I couldn't do it all, and I was okay with that. I just like, you know, solving a few more puzzles. And he wasn't so fond of that idea for some reason.
Yeah, that seems very odd to me because math to me seems like a practice, kind of like learning a language
Exactly.
or any, yeah. So, the more you practice, the greater your skill will be. I mean, maybe he had a different perspective, and maybe he thinks that people have just innate math abilities and some people don't, but I don't know. It's very interesting to me.
It remains a bit of a puzzle to this day.
Yes. So you mentioned that you were able to have more kind of free flowing, interesting conversations with one of your other teachers, one of your other science teachers, and you began to speak to her about your interest in astronomy. So what was what was influencing that interest? Was it just, looking out at the night stars, or was it something that you read about, or something to that effect? What broached the subject of astronomy for you?
Yeah, that's something that remains a little bit nebulous to me. But I remember sort of bits and pieces of it, namely that in again, summers, we would go camping, and it's obviously dark at night, limited light sources, and I would just look up to the stars like, oh, there they are, the little lights in the sky. So these are some of my earliest memories. My dad also took me to a small telescope, that the university, I think, operated in my town, and once a month or something, people could take a look. That was already, though, after I kind of knew I liked stars, so he wanted
Okay.
to do something nice and take me there. So that wasn't sort of the ignition of things, but certainly in the summers, looking up and ahead. And then I've written a little bit about this in my book, that I had to take the bus home from school, and it was two buses, actually, one going into town and then one going to my house. And I had to often wait in town for the second bus, and the bus station was right by a bookstore, and they had all sorts of books laying around. They had these tables outside, and I would like to just kind of go look at the books because, again, I had nothing better to do, no phones to play with, no nothing. And they regularly had astronomy books there. And so I started looking at these books, and I could understand nothing. No, I had time really to read anything, but I like to look at the pictures and read the captions about planets and stars and galaxies. And of course, that was in the 90s. The wealth of data and images we have from telescopes now is extraordinary. It was almost
Yes.
next to nothing back then. But it was enough to spark my imagination. And so I repeatedly had these sort of 7-minute excursions in this bookstore, sort of my early equivalent of Google, doing an image search, that 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 I felt very comfortable with, just reading a little headline here and a little headline there, and just seeing these images and sort of being sucked in, thinking like, wow, what does it mean to see a star and to be a star, right? And sort of what goes on in the star, in the core of a star, for example. Why does it shine? And eventually I got gifted some astronomy books because I requested those, and so I started to read a little bit more about it. And so it was just sort of little by little, very very gently, I would say. Nothing too much in depth, but I always felt kind of connected.
Yeah, the night sky is just fascinating. I lived in the suburbs, so I wasn't always able to see a full. I don't know if I've ever seen a full sky of stars, but I
It's
was
very
very interested. It is very hard. But I was very interested in stars as well, and I had a telescope, and I loved going to the planetarium. So it's
hard.
very inspiring, I think, just to think about those stars out there, just kind of doing their own thing and nothing very concerned about what's going on here in Earth, and just the magnitude of space and the distances and everything that's there. So yeah, it's amazing. So what you're describing is very salient to me, at least.
I never had a telescope. I guess I'm compensating for that these days by using the really, really big professional glasses in South
Yes,
America.
yeah, which we definitely should get into. Yes, very soon. So, as you were moving through your secondary education and into post-secondary education, what was that process like for you? How did you think about those steps? And did you have maybe mentors or people to support you along the way?
I did, and that made all the difference. I met some professional astronomers through a student conference that I participated in high school, and they were very kind, and they were the first ones who really took me seriously with my interest, besides that chemistry teacher. And I was really fortunate that I was kind of at the right place at the right time, meeting the right people who said like, okay, I'm listening. I love that you have this enthusiasm. We're happy to help you, learn a few more things. But let me also tell you, do this and this and this. If this is the path that you are eyeing, um, this is what you have to do. And that was to study physics in college, and then later on specialize in astronomy. So they made sure that I had no false impressions of, studying astronomy.
Okay.
uh, there's no real value of having a degree in astronomy. And it doesn't even make all that much sense, because you just got to sharpen your overall physics intuition and learn how to handle math and equations and physics and all of that, because that's kind of the fundamental baseline from where to start. And it doesn't matter if you want to do biophysics or condensed matter physics or astrophysics or anything. You just got to learn the language first, right?
Right.
And so that was good advice. Wasn't exactly what I wanted to hear, because I wanted to do astronomy right away, because I was so enthusiastic about it. I was like, okay, it's like, chill, you'll get there. But if you want to do well, you got to do it right. And that was good advice. It was advice at the right time, and it was firm enough, but nice enough that I was able to take it. Because sometimes we do actually get good advice, but we're not really ready to receive it. Right? There's broadcasting and there's receiving.
Yes.
And fortunately for me, and we wouldn't be speaking right now to each other if there would have been a mismatch in broadcasting and receiving. So
Definitely.
I remain very grateful. And actually, just a few weeks ago, I was visiting with one of these astronomers again, because we have remained friends for 3 decades now, almost. So this is really nice. This is
That is
really
really
nice.
nice. Yeah.
But I want to just clarify again, this was a very fortuitous circumstance that I somehow, found myself in, because there was this astronomy course offered at that conference I attended, and that it sort of all fell into place. But I wish for others to have similar experiences.
Definitely. It can be challenging to find mentors and, like you said, have that right timing and not have the mismatch, whether it has to do with time, like people not having enough time to meet together, or like you said, just not having the ability to receive what they're saying. So I hope that there are more mentors out there for the next generation of astronomers who are coming out. Uh, so as you moved through college, then did you go straight to graduate school right after college?
My situation is a little bit unusual in the sense that I did not officially finish my undergraduate degree in Germany. Now, it was a very different degree at the time. It was almost like a master's, so 5 or 6 years, with several years of classes, and then a master's degree thesis. I did do 3 years of physics, of classes, coursework. And then I decided, like many others, to do a year abroad. That was a very popular thing to do at the time. I don't Probably still is, just to see something else. And I decided to go to Australia. And again, with the help of my mentors, that became a possibility. And so I ended up at Mount Stromlo Observatory of the Australian National University in Canberra in Australia, uh, initially with a plan to do one for 1 year, and then to return to finish my degree. Now, sometimes we have good intentions. In my case, um, it this year that I spent there went so well that they offered me a position in their PhD program, and
Oh,
said, well, you have an equivalent of everything that an Australian degree offers, which was correct. We'll take what you have, including that year of doing two research projects and writing kind of a thesis about it. And so I made the very, very difficult decision of not returning, but to stay and to pursue a PhD. So from a German perspective, I did not finish. From an Australian perspective, that was just the normal progression of how science careers are set up. So it depends a little bit how you want to look at it. But that's how my cookie crumbled. And so I then stayed on for another 3 years and a bit to do my PhD thesis, which again was sort of the typical length, 3 to 4 years for a PhD in science in Australia. Very different than in the US, much shorter, but that was the typical path there. Yeah.
And how was your PhD experience there? What did you study?
It was wonderful. This original feeling of, wow, I see the stars in the book. I wonder what story they have to tell me. This is what I lived in Australia, because I started to work on old stars, the oldest stars in the universe. I still search for them. Occasionally I'm finding some. Two different things, right? Searching and finding. But both my search and my finding certainly began when I learned to use a smaller telescope in the Australian outback. That was really quite marvelous, being able to operate the telescope, being for the first time seeing the southern night sky, which is much more beautiful than what you can see in the north. In the north, what we see on the sky as this milky band is actually the next outer spiral arm. So we live in a spiral disk galaxy. The Milky Way is a disk galaxy, but the disk isn't like a solid disk. It has a spiral structure. So when we look at the night sky, we see the next outer spiral arm. We're looking right into that. And behind it is nothing but blank, dark space. So in the north, we see, the little lights in the sky, but really all we're seeing is the spiral arm. In the southern hemisphere, it's a different story because we're looking in the different direction, in the opposite direction. So we're looking to the next innermost spiral arm, and that is backlit by the galactic center. And that's bright. It's compact, but it's very bright. And it creates these wonderful structures of light and dark all across the sky. Is absolutely marvelous. And so in Australia, that was the first time when I saw that. I had seen pictures of it before, but it was very different to see indeed now the entire sky, because I was in an observatory with no trees. And to literally, actually at the time it was still allowed to climb on top of the telescope because it had a weird square dome, and I could lie on top of it and just literally see it all like in the movies, right? Above you. And so that changed me for the better. I like to believe. seeing all of that. And I was actually just working on the chapter describing that for my upcoming book. It is so nourishing for the soul to see the sky and the connection with the universe, because now, when you see that, and you can close your eyes right now and imagine this, you're looking into the next inner spiral arm and you see the galactic center right behind it. You can feel that you're part of this disk that makes a Milky Way. The Milky Way becomes a thing. It has dimensions and we're living in it, right? It's not this abstract thing that's somewhere, oh, there's a galaxy called the Milky Way. Well, yeah, but we're part of it and you can see it, right? And I had this sort of light bulb for the first time when I was there at the telescope, really feeling that I may be small, but I'm a part of it, whether I like it or not. and that can be quite eye-opening.
Yeah, I mean, it's a little overwhelming because, again, just the sheer magnitude of just our galaxy, and we're just one of billions of galaxies. But we are part of this enormous whole that, and there's just so much beauty to it as well, too. Just what you described.
Absolutely.
I can only imagine how beautiful it was just to sit under those stars, and even peaceful to a certain extent, to kind of feel like,
Absolutely. Absolutely. Yes.
yeah.
It is a bit, it's certainly transformative, because you come home slightly different person, but in those moments I didn't actually really feel the distance anymore. It was just, I
Mhm.
was just there, kind of in it, the full immersion. And there's a lot of art that tries to recreate this kind of feeling, right, of getting
Mhm.
sucked in to some degree, right? And it this definitely happened to me, and not just then. It has done so many times afterwards.
So how, if maybe it's a little difficult to describe this, I'm not sure, but how close are we to the galactic center? Are we close to the outer edges? Are we kind of in the middle, or closer to the center?
Yeah, we're about 2/3 on the way out,
Mhm.
and that's a good thing. There is a supermassive black hole in the middle of this galactic center region, and we don't want to be too close. um, yeah, so we have quite a good vantage point, I would say, and also again, so being far away means we can really see it all, and
Mhm.
and so we do get a good view of of a large part of the Milky Way.
Mhm. Great, great. So, can you tell us a bit about how you ended up at MIT, like just your journey from Australia to MIT?
Yeah, I finished my PhD in Australia by finding several really important old stars, and we can talk about that in a moment. What that means
Mhm.
and why that's important. But these discoveries really helped me to establish myself as a professional scientist and astronomer, and that enabled me to to go to the U.S. for postdoctoral work. So that's the typical pathway. You first do your PhD, and then you seek postdoctoral work at other institutions to do more projects, to really stand on your own without an advisor, um, or at least not a very close advisor. And then eventually you apply for faculty jobs, and in the best case you become a professor. And so that's exactly what happened to me. I was a postdoc in Austin, Texas, at the University of Texas there, for a couple of years, and then I moved to Harvard, just up the road from here, and I was a Clay postdoctoral fellow there for 3 years at the Center for Astrophysics. That's a very big astrophysics research center. Um, and eventually I applied for faculty jobs, and I really liked MIT, and somehow MIT liked me enough to make me an offer. And I actually began my job talk here with a picture of me in front of the telescope in Chile that I had been using under the Milky Way. And
Ooh.
I said, I love telescopes. I love the southern sky. This is where my targets, my stars are. You have access to this telescope too. Maybe we can work something out. So um, that's the only thing I remember about that talk. The rest is a total blur. But that was my introduction. And that is what I have done ever since coming to MIT. I have used the same telescope in Chile, so no longer in Australia, but in Chile, again under the same sky, seeing the same stars, and searching for and sometimes finding the oldest stars.
Well, sounds like an incredible journey, and you must be really at the top of your field to be at MIT and doing what you're doing. So this is an honor to be able to speak to you about the oldest star. So, can you tell us a little bit about your research on the oldest stars in our galaxy? So, what makes these stars so unique and interesting to you? and to others for that matter.
Yeah. Let me start by saying that our galaxy is mostly full of young stars. The sun is 4.6 billion years old, and for me, that's a really young star. uh, Usually, when we talk about stellar ages, we're talking billions of years. So that's our unit. So 4.6 for the sun. The universe itself is 13.8 billion years old, for reference. And so we are trying to find stars that are sort of 12, 13 billion years old. And that marks a phase in the universe when the first stars had sort of formed, and then the second and third and fourth generations of stars sort of came about, and everything else after that is less interesting to me for the following reason. And that's another sort of thing that I need to just wedge in here so we can understand the full picture. We are all made of different chemical elements, mostly hydrogen in the water, oxygen, H2O, right? We're 90% water, but we're also made from many other elements, calcium, iron, magnesium, everything in the periodic table. But all these elements kind of came from the Earth, but really they came from the gas cloud from which the sun and the planets formed. And how did it get in there? So all the elements were made in stars and supernova explosions and other violent explosive events that occasionally happen. And it started with nothing at the time of the Big Bang, because the universe was just hydrogen and helium. And then with every stellar generation, every star, certainly massive stars, big stars that explode as supernovae, more and more of the elements were created until we got to the point of the birth of the sun. And so a whole lot of stuff, well, a whole lot, a whole 1.4% of the universe was no longer just hydrogen and helium, but had been converted to heavier elements. And by now it's about 2 point something percent. So there is a chemical evolution that has been proceeding ever since the time of the Big Bang, where lighter elements are converted into heavier elements through stars in one or another way. All right, so how does this fit together now? We look for the oldest stars to probe an area in the universe when very little of all these heavy elements had yet been created. And that allows us to study exactly how the elements have formed. What came exactly out of the first massive supernova explosions that occurred a few 100 million years after the Big Bang?
Mm-hmm.
How did that seed the next generations of stars?
Mm-hmm.
How did it help to bring together gas to form the first galaxies? Until how long did it take for the universe to create enough heavy elements that you could actually make a planet? Stars are made, 98% or more of hydrogen and helium, right? So largely hydrogen and helium. There's a lot of hydrogen and helium in the universe, but not so much of all the heavy elements. Planets are, the Earth is almost exclusively heavy elements. You couldn't have made Earth on day one in the universe. It took quite a lot of time. We don't actually know yet what time, what the exact sort of transition was when planets could form, simply because there was enough material there to make planets.
Mm-hmm.
So old stars allow you to study the chemical composition of the earliest gas that there was, because they preserve in their outer atmosphere the exact composition of the gas from which they're formed.
Mm-hmm.
These stars have done nothing but sit in space doing nothing. They have a little bit of hydrogen to helium burning in their core, but the outer atmosphere couldn't care less about what's happening inside.
Mm-hmm.
Because little stars do not explode, they live almost forever. So the sun has a lifetime of 10 billion years. Stars that have less mass, and that's a weird thing, they live longer. So the stars that we're primarily looking for have lifetimes of 10 to 15 billion years. And they're at 13 billion years now. So they still have, let's say, if they have a 15 billion year lifetime, right? They still have a little longer to go. They're not going anywhere right now. And they have preserved in their atmosphere the exact composition of the time when they formed in the early universe. And that's why this work is called stellar archaeology, because we're digging out the secrets of the past. And we don't need to look very far. These stars are in the galaxy. It's like genealogy a little bit, right? We're asking our great grandparents, so to speak, what happened back then? Tell me, what was the world like at that time, right? What was the composition back then? What were the physical and chemical, what was the situation back then? So the light of these little stars has only traveled a few thousand years to us. We don't look for far away galaxies or anything. That's very complimentary work, but done by others. These stars are live and kicking right now, not far away, and they just have preserved this information for us very patiently.
That's very interesting. I was actually going to ask you about the lifetime of these stars, but you went into that. So if they're less massive, I also assume if they are heavy element poor, then they have longer lifespans, or is it just the mass that
That's
could
just
change?
a mass.
Okay.
Mass does matter.
Okay.
Very importantly, the first stars, that's another interesting tidbit that's quite relevant. It was actually not possible to make small stars from this primordial just hydrogen and helium matter after the Big Bang. So the first stars were very massive, and their lifetimes were only a few million years, and then whoosh, they went supernova very, very quickly on cosmic time scales. And so that's how the first elements were seeded. And that meant the universe was changed forever, because the whole gas physics, everything changes once you add a little salt to your soup, right? If you cook water, it tastes like nothing. As soon as you add a little bit of salt, there's no going back, and it will taste very differently. And exactly that happened with these first explosions, and that allowed for small stars now to form. And they are the tracers, the probes that have the capacity to live for billions and billions and billions of years, all the way to the present day and longer. And that's really lucky for us, because they just carry that information for us ever since.
Yeah, that is very lucky for us, because if they all had just become supernovae, we wouldn't really know much about what happened in the beginning.
Exactly. There would be, we could not preserve anything.
So you mentioned the chemical composition of these stars, and that it's remains fairly constant for at least the part of the lifetime that we were able to observe. What is the chemical composition? You mentioned helium and hydrogen. Are there any other gases that are present in those stars, or is it just kind of the ratio of helium to hydrogen?
Great question. So the very first stars were just hydrogen and helium, and then for energy generation purposes, they cooked up heavier elements in their cores, all the way to iron in the periodic table. So all the lighter elements, carbon, nitrogen, oxygen, calcium, magnesium, chromium, nickel, and so forth, all the way up to iron. Well, actually, nickel is technically heavier than iron, but to zinc. We get everything up to zinc. And that material was expelled into the surrounding gas. And this is exactly what we then find in the atmospheres of our little surviving stars that we observe today. So all the elements are there. And actually, more so, we also find really heavy elements in some of them. And that means if you now think backwards, so we have an old star. It has very, very small amounts of these lighter elements up to iron and zinc. And then we have a relatively much larger amount of heavy elements like strontium and barium and europium and silver and gold and platinum and all these fancy elements.
Mhm.
And you're like, where does that come from? From what kind of gas cloud must my star have formed
Mm.
so that I'm seeing this kind of pattern right now?
Right.
Right. And so that's my actual job, to kind of
Mm.
figure out, come up with idea, being creative
Mm.
of figuring out what must have happened to that gas cloud that later produced my star
Mm.
so that I see what I see today. Right? What kind of pattern can there be? And to give you a hint of a solution here, these stars that have such high levels of heavy elements,
Mhm.
it probably means that a pair of neutron stars, which are not even real stars, just giant, very dense balls of neutrons that are
Mhm.
the leftovers from supernova explosions. If you
Mhm.
put two together and they orbit each other,
Mhm.
eventually their orbit will decay and they will in spiral. They will merge, and
Mm.
imagine you merge two metal balls,
Mhm.
right?
Mhm.
Violent explosion, and it takes neutrons to make heavy elements. There are only very limited ways you can create heavy elements, and it involves a lot of neutrons on a very fast time scale. And so that naturally happens when you merge two neutron stars, because it's just neutrons galore.
Mhm.
And so probably an event like that occurred in that gas cloud. Heavy elements were made,
Mhm.
seeded into the gas, then my star forms, and then presents me with the puzzle 13 billion years later as about what happened.
Oh, very interesting.
That's one really cool example.
So does that mean, because neutron stars are still forming, because supernovae are still occurring in the universe, so does that mean that this process could be happening now? Where
Yes,
they're okay, very
absolutely.
interesting.
Neutron star mergers happen, I want to say, regularly, but not frequently,
Mm-hmm.
because it takes quite a while for most of these systems to in spiral. They lose their energy very slowly. And with gravitational wave detectors, which is sort of the latest and greatest in astrophysics, that we
Mm-hmm.
can now detect that is a big deal. And
Yeah.
one neutron star merger was indeed detected several years ago in 2017, where this exact happened in the local universe.
Oh wow.
So not a long time ago, very recently for us in terms of the detection, but also
Sure.
cosmically speaking. And that was confirmed that that is a thing. That it was
Wow.
theory beforehand, but that showed clearly that that's a thing, and it makes heavy elements. And I was like, yeah, I've seen that. 12 billion years sooner than that, but that's a thing.
That is so interesting, and also just to see that you're looking back in time and you're seeing it, but people are also studying it today and making certain observations that are newer, like the gravitational wave observations, and
Yes,
being
yes.
able to confirm that that happens is really really cool. So I guess that brings us a little bit into the next question. So about the techniques that you use to identify and study the stars. So what are those techniques?
I'm a spectroscopist. And to keep it simple, what we do is we basically take starlight and turn it into rainbows. When you see a rainbow, it means that the light has been split up into its rainbow colors. We do that with the help of a spectrograph, and uh, what we then record is not just the rainbow spectrum, or what we get is not just the rainbow spectrum. It is a little bit more than that. Namely, there are colors in the rainbow that are missing or partially missing.
Mm-hmm.
And what that means in terms of the physics is that it gives me clues as to which elements, which atoms, types of atoms are present in the stellar atmosphere. And atoms have the the property of absorbing light at certain frequencies. So that
Okay.
translates into wavelengths, and that's the missing light that I'm recording.
Mm.
And that happens in very specific sort of sets of colors that are missing per
Mm-hmm.
atom.
Mm-hmm.
And from that, we can puzzle again backwards. If I see this and this feature in my spectrum, in my recording, then that means that that and that element must be present,
Mm-hmm.
and it is that abundant or not.
Right.
And this is how we determine the chemical abundances of the various elements to then establish, okay, my star has this and this pattern. And then, again, it's up to us to figure out how did those elements get into the star.
Very interesting. And the stars that you study, they're located in our Milky Way galaxy.
Yes. Some are really quite bright. And a long time ago, an amateur astronomer was inspired by an old star that I had published, and he took a picture of it and sent it to me.
Oh.
Now, actually, I'll be honest, a picture of one star is actually quite boring because it's just a blob,
Right.
in the universe. Many more stars together can deliver you nice pictures, but that is also one nice little hook in the sense that we can only get so much information as astronomers from taking pictures. Now, that's important information, but you get a lot more information from taking a spectrum because, again, that offers you the opportunity to learn about the composition. What is this thing made of? Which is a really fundamental question, right? We ask that of everything. We ask that of ourselves. What is our body made of? To some degree, we ask of people, sort of, what are you interested in, right? What are your views? What are you made of?
Mm-hmm.
But of course, we also ask it of the universe itself. What are you made of? And so that adds a really important dimension to what astronomers can provide.
Very interesting. So the stars that you study are near to us relatively because they're in our galaxy. But in general, are these old stars distributed throughout the universe, the observable universe, somewhat uniformly, or do they tend to be localized in certain areas or something in between?
Yeah, I expect there will be old stars in every galaxy. The spectroscopy requires this is sort of a very detailed way of observing, so we cannot look too far out. So we cannot really see and study stars in different galaxies that way. So I can only speak to the Milky Way, but the work over the past several decades has very clearly shown that the outskirts of the galaxy is where the old stars live. And we already talked a little bit about that. We live in this disk galaxy, and the spiral arms host most of the stars of the Milky Way, of our galaxy. But there are stars that are, you know, above and below the disk, and we call that the halo. So the disk is sort of enveloped in a a bit of a sea of stars, really. And I often call it the junkyard of the galaxy. um, because what do you find at the junkyard, right? Old stuff that came from somewhere else. It's just collected there. The stuff in the junkyard is not from the junkyard. It's from somewhere else. And the same is true for for what we see above and below the disk. That stuff came from somewhere else. And you have to ask yourself, like, where did that come from? And if we take a second to think about how the Milky Way actually evolved, the Milky Way itself is a big thing. It wasn't always that big. It started off with the first stars and the first galaxy as a small blob that grew. And how did it grow? It ate up its neighbors. Survival of the biggest. Because if you were a little bit more massive in the early universe, you had a much easier time gobbling up the less massive stuff simply because of gravity.
Mhm.
Mass goes where more mass is. Gravity is attractive.
Mhm.
So the Milky Way grew by eating up its neighbors, and that meant that the old stuff and it did so while the disk of the galaxy was forming. So whatever got eaten, kind of ended up in the outer parts. Certainly anything eaten at later times. And so the old stars that we are observing today are in the galaxy, but they're not off the galaxy. They came from other little dwarf galaxies that, were innocently surrounding this proto Milky Way, and then they got eaten. And the Milky Way still tries to do that, right? So we're orbited by a number of small dwarf galaxies, and some you can see they're no longer round. They are cigar shaped now because the Milky Way is trying to pull the stars out of it. It wants to eat it.
Wow.
So we can see that in action.
Yeah.
Slow action, but nevertheless, yes.
Yeah, it's such a dynamic process. And it's interesting. I know that there's, because I spoke to another astrophysicist who studies black holes, and I know that it's an open field of inquiry about just the formation of galaxies themselves. And it's just interesting to me because there's this massive black hole in the center. And I assume that there must have been at some point, maybe a slightly smaller black hole at the center, but just that how, the stars were able to be attracted. Some of them probably entered into the black hole, but many of them didn't. And whatever the dynamics of that system is enough to actually form the galaxy as opposed to just everything collapsing into the black hole.
Absolutely. That was probably quite the balancing act. I guess the black hole was never like really super active. Basically putting the vacuum cleaner on high, sucking it all up. So that's lucky. Also, right now it's doing its thing, but it's not on high right now, and yeah, that's a good thing.
That's good for us. Not trying to get sucked into a black hole anytime soon.
Yes.
So I have maybe another speculative question. So there seems to be kind of an evolution process with respect to the chemical composition of the universe that you're studying. And maybe it has some parallels to evolution of life here on Earth in terms of there are some periods in evolution that are necessary to form complex life forms. So, for example, moving from prokaryotic organisms to eukaryotic organisms is kind of a prerequisite for more complex forms of life. And so, do you see similar periods in kind of the chemical evolution of the universe that are necessary in order for the universe to develop to what it is today? And if so, are you able to observe some of those chemical signatures in the stars that you're studying?
Yeah, this is a really interesting question, and to some degree, I alluded to that already. I think two things come to mind, and one is again simply amounts, right? If you wanted, if you again look backwards, if you want to look for, if you consider life on a planet, you got to ask the question, how did the planet form, and what's special about the planet that would then later enable life to form, right? And we don't know right now when the threshold was crossed that enough of the elements were there in principle to allow planet formation. So that's an ongoing question, but rather than a phase, I would say that's really just a big stepping stone. That this threshold needed to be crossed, otherwise we have nothing. We literally have not enough. Related to that is, of course, the relative abundances of all the elements that then feed into what life requires. There is, of course, carbon, nitrogen, oxygen, phosphorus. I forgot, there are a couple more, the elements of life, right? The most important ones. And they had to each get made and each in different processes and on different time scales and by different objects. So that is also, a necessary condition for that to also work. So there's overall amount of heavy elements to get sort of gas cooling processes working and clumping and accretion to physically, dynamically make a planet. But then, of course, the next question is, what are you going to sprinkle into that? And, what is it supposed to be made of? I mean, the planets in the solar system all have very different compositions, actually. And it's still absolutely unclear how on earth this all worked. So elemental composition is a very big part of that. Now I can tell you that a carbon is very easy to make in many different ways. The universe did not have a problem making a lot of carbon. And actually, even early on, I believe carbon is the most important element in the universe besides hydrogen, which is just protons. I mean, sort of the building blocks of everything. So that aside, carbon has extraordinary cooling properties in the gas and most certainly played a vital role in creating a situation in the gas that it could clump and form these very first small stars that then had these long lifetimes. So without carbon or this exact atomic structure that enables this cooling, everything would look different right now. And then, of course, we are made from carbon, so that has meaning. So carbon gets the check mark. Other elements are much more difficult to make, but almost 10 years ago wrote a paper on phosphorus. So we looked at the chemical evolution of phosphorus, for example. That's very important for energy generation in the cell, and we could kind of nicely follow how it also had increased with time, although the exact production mechanisms are actually not well understood. But at least we could map out, sort of in hindsight, I mean, we know that phosphorus is here and that it's important, but we wanted to really kind of see to believe, how has phosphorus evolved over time to what we have available to us right now. And so that was kind of cool. And so for most elements that has been mapped out. That is what we observe. It doesn't mean that we fully understand how this exactly happened, but that's part of the ongoing research that we're all doing to kind of brick by brick fill in the wall of knowledge. Yeah.
That's very interesting. So what successes, and I think you've alluded to some of this, but maybe you can talk about it a little bit more. So what successes have you experienced in your work? And then also what challenges do you face?
I have been lucky enough to find a number of interesting stars that helped exactly, eluding the processes I just try to describe. Again, how the first stars formed, what the first galaxies looked like, how the elements evolved over time. And that has been a lot of fun. and also simply of interest to many people. And I think that is how success is mostly defined, how much interest other people take in it. But that's not to say that, anyone else's work has been less important. So I think we need to be a little bit careful about, what we call successful and what we call important. It all adds up. I mean, ultimately, I think success is when we learn something new. Some results are hyped a little bit more than others, often because they are communicated perhaps in different ways. And so the topic of old stars has always lent itself to good storytelling, and people can relate to it. And so I have very much enjoyed telling these stories, and that has always helped my career. There have, of course, been challenges along the way, but I would say I've always had really great mentors. And so when things were kind of slow, or I didn't really find what I thought I had found, that wasn't such a big deal because it was like, the sun will shine again tomorrow. That's yet another star. Um, it will all be okay somehow. So I know many other women in science really face quite significant challenges. Um, Luckily for me, I haven't really had bigger troubles than having, proposals rejected, of course, sitting at the telescope in the rain, and I would go home empty-handed. Um, I mean, I'm a single mother with 2 kids. My days are busy. That's a different kind of challenge. So that's
Definitely.
not a roadblock of any kind. It's just how to get it all done. And I feel um, I don't want to say I feel challenged every day, but every day is a new way for me to brave my day and to carry out all the things that I wish to do. And it often doesn't work when when something is required at home. Then that has to be dealt with, and that's just it. I'm pretty sure many people can relate. And
Mm-hmm.
so this sort of stretch between, oh, I want to be there for my children, and I want to be there for my stars, and I want to be there for my students and my work. That's taxing at times. Um,
Yeah.
but I consider that sort of a normal part of life. At least I made my peace with that, even though it's hard sometimes. I'm not going to sugarcoat that.
So my question was about AI or other types of related algorithms. How have they or will they influence your research or your kind of your area of study?
Astronomers have used machine learning for quite a while. So this is not new. What's new about it is that people are talking about it and talking about it in a different context, mostly about the large language models and writing, whereas we have used this for number crunching for at least a decade. Um,
Very
the
interesting.
thing with machine learning is that the computer can only know what we tell it. It is not actually intelligent. It can do all sorts of clever things with information and numbers, but so can
Mm-hmm.
math. um, so it knows exactly, it lives in machine learning is a box. You feed it certain things that determines the size of the box, right? And then it does its
Mm-hmm.
thing in the box exactly how you define the box.
Right.
And we have been using this for a while to classify stars and galaxies, and to we do that. The technique is fairly simple. You train your system on a given set of stars, and that defines the
Mm-hmm.
size of the box, and then
Mm-hmm.
it can really well identify stars that fit within that box.
Okay.
And
Very interesting.
for my work, this is all the normal younger stars that have accidentally not been selected out, because we have to select out, we want to find the needle in the haystack. And so it helps us here and there to find all these stars that we don't want. uh, and then we're left with the stars that the program doesn't know what to do with, but that's
Mm,
because that's are the outliers that live outside of the box,
right.
and those are the ones that we want to have. So we've been kind of using it in reverse,
Mm-hmm.
quite well. And so it's been useful. And again, with all of these tools, you get out what you put in, right? You
Right.
define the box, you know what the box is and what lives in the box and what lives outside of the box. And the more well-defined your question is of the box, the better the answer is. Now,
Mm,
most of us sometimes get a little bit lazy with asking good, clear questions that actually can be answered.
mm,
And this is where it gets kind of interesting, in a sense that sometimes we ask a little bit too much of the box, because the box
mm,
is very simple. The box is exactly how we define the box to be. So if we leave that and go too far away from that, we may be getting answers that no longer really match the question, and then then we may be subject to interpreting things um, a little too wildly as we perhaps should. So I think that is for me an issue with AI, that it really invites you to ask really big questions that we're not quite ready to answer because the tool is still fairly limited, right?
Yeah,
Um,
that makes a lot
but
of sense.
we'll figure this out collectively. And I
Definitely.
think that's a job of a scientist, to think really well and deeply about what question can I ask of my experiment and what can I not ask of my experiment. What
Hmm.
do I need to design a different experiment for my other question, and to be very clear about the distinction.
Yes, definitely. That makes a lot of sense, especially with machine learning, because computers can compute very fast. They can sometimes do calculations that we may not be able to do ourselves very easily. And with machine learning, especially, can kind of find correlations that might be more difficult to find, again, just with our own calculations. But like you said, it's all based on what you put in, the data that you put in, and the knowledge base that you give it. So, yeah, that makes a lot of sense. So, my next question is from Dr. Renee Hale, whose interview will come out later this fall. She's a chemical engineer. And she asks, what is the hardest part of your job and how do you tackle it? And I think you kind of alluded to this, but maybe you could discuss it a little bit more in depth.
Um, Sometimes the hardest thing is getting out of bed in the morning. uh, um, I mean, hard. It's actually, yeah, I find it difficult to answer. Um, because there are always hard parts, every day, and every phase of a project. You come across stuff that you aren't prepared for, that you feel not ready for, that is unexpected, is at the wrong time or the wrong place, and you're like, oh, not now, right? So, but this is also what we're asking for as scientists, right? Because if we
Hmm.
had all the answers, then we'd be out of job. So
Yes.
in some sense, we are troublemakers by design. Um, and yeah, so, I want to encounter the hard things, but it is hard to persist through that and to say, like, okay, I put a lot of time into that, but it's not working. Let's try something else, right? That takes strength and mental energy, and that can be physically hard sometimes, in addition
Hmm.
to being, let's say, disappointing, perhaps. Yeah, so, but it's also what I really like about this job, because I never know what I'm going to find tomorrow, whether that's something I like and it's like, oh, this works, or it's like, oh God, back to the drawing board, right? It keeps it varied, and my brain likes this.
Very good. Very good. Thank you for sharing that. Um, I think that it's rewarding, even though it's hard,
Yeah,
the
yeah.
reward is built in, it's intrinsic to the process. So.
We can all do hard things. I keep
Mhm.
telling that to my kids. But
Oh, that's great.
it's great.
Yeah. So I just have a few kind of random questions, just to get to know you in a different light. So we were introduced by Jen Miranuk from STEM on Stage, and I will be interviewing her later this fall, along with Susan Marie Franchek. So you're doing a living history production uh, with STEM on Stage, where you will portray Dr. Lisa Meitner. So could you tell us a little bit about this production and what inspired you to take on this project and this role?
Yes, that's sort of one of uh, my hobbies, in the sense that I have a really full plate, but I just like to do science related things because they spark joy. And one of the so what the what brought us there is an interesting story. So years ago, I was invited to see the digital humanities show, Marie Curie, a visit. Sorry, Humanity Needs Dreamers, a visit with Marie Curie, that Susan Marie Franchek portrays. And so it's a digital film theater presentation that was absolutely remarkable. And so it was 45 minutes long or something, and we were sitting there following hearing about the discovery of radium that Marie Curie made some 100 years ago. And I always had looked up to Marie Curie as a female scientist, and here's of course the cool thing: she discovered a new element. And what do? I study heavy elements from the bottom part of the periodic table, including uranium, by the way, and thorium, also radioactive elements, in my stars, right? So Marie Curie has been sort of with me ever since I was a teenager. And here I see this presentation of this woman on screen reliving this this discovery process and what it took to get there. And then the film ended, and then Susan Marie stepped on stage in costume and to take questions from the audience as Marie Curie.
Oh.
And I was like, oh my God, she's standing right there and I'm here. I was transported back in time, teleportation and all. It was a marvelous moment because I was so immersed in the story of this discovery and hearing from this woman, and then she stands like right there and like moves and says things. It was a very moving moment for me. And afterwards, I came to talk to Jen and to Susan Marie in costume, and I said, well, fantastic. How about you take on other personas as well? Lisa Meitner would be a really interesting one. And Susan Marie was like, yeah, no, but how about you? Or maybe Jen said it, you should do that. And I was like, yeah, right. But that was sort of when the idea was born, that certainly for me, that we need to hear from many more female scientists, right? I mean, right now I just watched Oppenheimer at the movies. This is a great science film about a male scientist. There have been many films about great male scientists. Great to hear. But how about providing scientifically and biographically accurate science films to the public to provide, this kind of, to fill in these missing gaps that we have all across history. So here we are at the moment where it's very important to look backwards, and recognize what we already know and what we don't know yet. And I think too many stories of female scientists remain untold to this day. And that's why my first reaction was like, I want more. And they're like, yeah, we too. But we only have 24 hours in the day. So then some time passed, and nothing really happened. To cut a long story short, my mother had always given me biography books of women scientists when I was a teenager, and one had been Lisa Meitner, and that's why I knew about her. And she and I collaborated a little bit on an early script to do a 15-minute theater presentation for myself to trial this, because I was like, hey, I've done theater in high school. I can do that again. Let's just do something kind of crazy. Try something new. And then I later on translated it from German into English, and then Jen and I further worked on the script. And occasionally now I do a 25-minute theater presentation as Lisa Meitner, reliving the moment of discovery when she figured out what nuclear fission means, so how energy is released when you bombard heavy elements with neutrons. And then I turn into myself and I give a presentation about the origins of the heavy elements in the cosmos, and how that all kind of connects, and what our cosmic origins are. And it's quite enjoyable.
It's such an exciting project, and to be able to link two women scientists together with your own work, first of all,
Yes.
and then second of all, to be able to share the connection between your work and Dr. Lisa Meitner's work. So it's a really exciting project, and I hope it gets out to more people,
I
so that
hope
they
so too,
can
yeah.
learn more about these women. So you have kind of your research program, you have your professorial duties. You're also the head of the Division of Astrophysics at MIT, and you're doing these other projects, and you've also started a program called LEAPS in order to support graduate students in their transition into their academic careers. So tell us a bit about this work. Why was it important, and maybe a little bit about the impact that it's had?
Yeah. So you already asked me the question, how did I come to MIT? There's a sort of a related question that people often ask me. What did you need to master in order to be considered for a faculty position, especially one at MIT? And prompted by this question, for a long time, I've been thinking about, okay, what does it actually take to be a scientist? Because I just was a scientist doing things, but I never really reflected much on what did I actually learn, right? And what am I perhaps good at or better at than other people? And in the process of that, which was a long one, a whole set of skills emerged. And to cut a long story short, that forms the basis now for this leadership class. So LEAPS stands for Leadership and Professional Strategies and Skills, because I have come to learn and believe that, of course, everyone is responsible for their own life and their own career. And there's much more responsibility that I think people can take to shape their own career in academia and generally sort of science fields, or at least their PhD and their postdoc work, than they often think. Academia is still a fairly hierarchical system. And often people, I think, enter it knowing that they're sort of at the bottom of the pile, as grad students. But I don't think people are quite as powerless as they sometimes are made to feel.
Mm-hmm.
And it's a really enjoyable class for me to teach. So it's for grad students and postdocs. And we talk about all the kind of soft skills that one should master, and how much, and at sort of what times, in order to just become more well-rounded, more efficient, but not for the sake of getting more done necessarily, but just sort of being more concise and more confident in how you approach things.
Mm-hmm.
And that's why the second half is certainly called, or purposefully called, about professional strategies, because you can do a lot with useful intent and purpose at the right time to kind of drive that wagon down the path that you want it to go. In my experience, many people feel like they're a passenger in a car, and they have no map, and they don't know where they're going. They're just hoping that someone kind of keeps pushing from behind,
Mm-hmm.
right? And my attitude has much more become, it's like, get in the driver's seat, here's a map, here's a compass, here's the fuel. um, Roll up your sleeves, look ahead, and go. And this has exactly been the impact that I can see people have the light bulb in the classroom, and I can see them move from the passenger seat to the driver's seat as they learn how to ask the right questions. They see, okay, I'm going to do that then. I'm going to stop at the red light and I'm going to go when it's green, not the other way around. And on the highway, I go fast. And in the city traffic, I will go slow and I will be patient. You can be impatient on the highway, hitting the fuel, in the gas panel. And that's a wonderful transition to experience.
Yes.
People start to talk differently. They start to strategize. They suddenly see their whole career in a new light because they know where to go and how to go about it. And we've done it for 4 years now. And it's really nice to see that really it has kept a number of women in academia because they could suddenly see the path. And they have been walking the path, and they have been well received because other people could see they have their walk with purpose and intent, and they're going to get it done, and they're enjoying it, and they know what they're doing. I mean, I don't mean to say that they don't know scientifically what they're doing, but they just walk in a different way. They carry it all with them right now in the best of ways. And they will make for wonderful professors one day. I'm keeping in touch with quite a number of them. And knowing that we've sort of found a way to move the needle a little bit, that is very heartwarming, really. And we have many people who have actually wanted to stay in academia. I should just add that, who have by now switched to industry. So we've had both. But they're also happier because somehow they realized academia cannot give me, now that I know what academia is about with the map and the compass in the car, maybe this is actually not where I wanted to go. Maybe I need to take a different route. And that's perfectly fine because we want for people to find their path. And sometimes seeing one path, you realize, oh yeah, that's what I want. Or maybe not quite. I'll try something different, right? The worst thing is to be on the wrong path or not knowing on what path you are. And so that is something that we clearly clarify with this class for, I would say, pretty much all the people who are there and who are willing to open themselves up to these kinds of discussion.
Yes. It's a great service, especially because a transition from graduate school to what's next is sometimes very difficult because sometimes all you want to do is just finish your dissertation. That's it.
Yes.
There's so many other things that you need to consider so that your career can continue.
Yeah.
So you're about to take a very special trip and a very exciting trip with a group of female scientists this fall. Could you tell us a bit about that trip and the impact that it's expected to have?
Yeah. So while I teach leadership to others, the learning never stops. And I am myself part of a global leadership program out of Australia called Homeward Bound. And as part of my own training, this program offers in its core a 3-week immersive training on a boat going to Antarctica for us to experience and practice really leadership under extreme conditions, cut off from the rest of the world, in an environment where we do nothing else but focus on ourselves in a way to how can we become the best version of ourselves, because leadership starts with leadership of self, then comes leadership of others, and then leadership in context. So there's sort of 3 layers, and the goal certainly is to really help us shape our leadership of self so that we become ready then for leadership of others. And we will be cohort number 6. So there have been several other cohorts before me. The pandemic scrambled things quite a bit, but we are finally going. And I've heard from the previous participants that it has been an absolutely transformative experience to be in this different landscape that is almost like a different planet. To have this time off from any and all distractions, no phones, no nothing, just focusing on self-discovery, collaboration with others, strategic planning. What do I want to do with my life? What I want to do in my work? What is going to be my legacy? These kinds of things. And to project development, all these kinds of things to really come home with a new mindset. And so it's going to be a big trip. I'm a little nervous, but I'm also super excited to expose myself to many new things, to get pushed out of my comfort zone physically and mentally, and to just let this pass through me and see what happens. Because I have to put my money where my mouth is, right? This is going to be my turn.
Yeah, that it sounds like an incredible trip and definitely challenging. Just doing your day-to-day activities is going to be a completely different way of having to be and do what you would normally do. So I'm sure that you're going to experience a lot of growth just from doing your daily activities, less more than also the other kind of more um, uh, leadership development and personal development activities that you'll also be doing. So I hope that goes really well for you, and that
Thanks.
you'll be able to share that with others, especially your leadership
Yes,
group.
yes, that's going to be very exciting. And I get to see penguins.
Oh, I'm
They're
so
wild.
excited for you that you get to see penguins. I love
And I mean, hopefully
penguins.
even more wildlife than that, but yes, penguins.
Oh my goodness. You're so lucky. So I just have a few more questions just to wrap up. So this next question is inspired by the podcast, The Diary of a CEO. And so what question would you like to ask the next person that we interview?
Yeah, I have often been asked, and so I would like to pass that on, what my feelings are when I sit at the telescope and I make a discovery, because it's quite emotional actually to make a discovery. When we publish papers, we only report on that the discovery has happened and what the consequences are. But this moment of discovery that was also so well portrayed in this Marie Curie film, and that I'm also trying to do with Lisa Meitner, is that nobody ever participates in that actual moment of discovery, because the publications have no room for that.
Right.
Nothing. And no, it's almost like a taboo. So I would like to know, when you had a big discovery, what did that moment feel like?
That's a great question. What did that moment feel like for you?
I could have anticipated that question. It's it is actually a little bit hard to describe. That's why I think it's a good question, because it's both relief and anxiety at the same time. It's relief, yes, I had the right hunches, I did the right things, it all kind of worked out. It was a long road. Whew. But at the same time, you're like, is that too good to be true? Is that really right? Did I really find what I think I found?
Mm-hmm.
And so there is this sort of time, this little phase in between, where you have to make sure that it's really true. And we all know of publications that had to be retracted because later tests and whatnot showed that someone was a little bit too impatient or too
Mm-hmm.
ambitious, right?
Mm-hmm.
And so it's this in between. So this phase starts with the moment of discovery that makes you a little anxious, right? And so you usually get more data and you run more tests and you discuss with more people. And so it really stretches you as a person to feel both of these things at the same time.
Mm.
Um, so that is what I would share.
Yeah. Yeah, it sounds like maybe there's a mixture of fear and awe.
Yeah, exactly. And
Mm.
it's really kind of breathtaking that you can feel both in the same moment, and
Mhm.
amply so.
Yeah. Must be incredible though. So, who else would you recommend that I speak to or interview?
Well, obviously, more women in science. Personally, I will say that I have never really closely worked with a woman who was more senior than me. I've only ever worked with much more senior men. And while these were all really fine people, I am good friends with all of them. They have always very much supported me. It was always guys. uh, and one of the reasons why I joined Homeward Bound was my hopes of connecting more with more senior women. And I'm regarded reasonably senior by now,
Hmm.
uh, even though I don't always feel like that. But hearing from not just upcoming young women, and I have been this woman for many years, it's very exciting to hear from, what's the hottest in science right now. But I think there's also a different, phase in a scientist's life that is covered by more senior people. And so I would, if I could make a wish, I would be interested to hear more about uh, from more seasoned women, and not necessarily about um, you know just about the successes of a longer career. I guess what I'm getting at a little bit is I recently got a book recommendation that
Hmm.
is about an interesting thing that I'm also noticing myself, namely that in the first half of our life, we're sort of in go, go, go mode, and we want to produce and we want to prove ourselves and we want to make all these discoveries. And I think us scientists were very much in that spirit. But then in the second half of life, we're a little bit more like, I've achieved all these things, cool, but maybe now it's time to step back a little bit and see the big thing kind of emerge from us and maybe become those mentors who can support the younger people. And so there's a bit of a transition. And so I would be really curious to hear from some senior women about sort of maybe they have experienced that kind of transition themselves. Maybe they're still in go, go, go mode.
Hmm.
The sort of about the bigger whole of the scientific enterprise. Um, so just some ideas. I think we need to
Thank you.
hear in society a little bit more about that sort of other side.
Hmm. Yeah, that makes a lot of sense. Thank you. If you could write a book, you could be either a children's book or an adult book about a well-known person in STEAM, who would it be about? I think I might know the answer, but maybe you have another answer.
Well, anyone goes really. Um, I mean, I could, of course, say, Lisa Meitner and Marie Curie, but I think we need to hear more just in general about these moments of discovery. And it doesn't really matter so much who that was. What matters is that people can associate with that feeling that is associated with that, right?
Mm.
We all want to achieve something in life. We all kind of crave to leave a legacy for our children. That's why people write memoirs, right? To leave
Hmm.
something behind. And a discovery is something that we leave behind.
Hmm.
And I I think, I mean, this is a really important aspect that I think children need to learn and to participate in. And then, of course, also the older children, the adults. What does it feel to discover something? Because everyone can discover something for themselves in life. You don't need to hack a scientific discovery necessarily. But we talked in the very beginning about broadcasting and receiving, right? We need to be open to making discoveries about ourselves. And so to use scientific discoveries as an example to highlight this process and how we can open ourselves up to this, of having these light bulbs, whether that's about ourselves or about the world around us. This is something that I'm actually writing about myself to some degree, not specifically, but it's certainly in the realm of what I'm working on for my upcoming book, to provide, to use science as a vehicle to provide a bigger perspective, right? It's life doesn't
Yes.
stop at the atmosphere of Earth. There is more, right? And
Mhm.
we need to broaden our horizon a little bit. We need to not just think about ourselves and our tiny little universe, right?
Mhm.
We gain so much from taking a deep breath and a step back and seeing things in a new light. Um,
Yeah,
so
definitely. Mhm.
that is certainly part of why I like science communication, to use this as a vehicle to help people to see that there's a lot out there and there's a lot to discover, and it looks different for every one of us, and everyone can find that.
Yeah, that sounds great, especially just to give that inspiration and to let people know also what the path might look like towards discovery. So that's great.
Absolutely.
So can you tell oh, so can you tell our audience where they can find you and learn more about the work that you do?
Yeah. So I have a website. People can find me on Twitter or whatever it is called at a given time. If you've been following that, um, I when I had time as a postdoc some time ago, I did write a book about my work. It's called Searching for the Oldest Stars, uh, because that's what I do most of the time. And as I try to tell you, once in a while we find something. So you can read about women in astronomy, because we all stand on the shoulders of giants, and a lot of women have actually worked in stellar astronomy, which is what I do. Uh, and so you can read a little bit about history, and then again how I'm adding to that story from a human perspective as well as a scientific one. Um, I have done a number of other podcasts and interviews. So if you put my name in Google, you will find a bunch of things. Yeah. So there are a few things out there about old stars, and I hope you all can learn a few things about our cosmic ancestors. They are good fun.
Well, great. Thank you so much for making time to speak with me today. Your research is fascinating, and your life path to get there is also very fascinating. Thank you for being willing to share both aspects of yourself, and as well as the other projects that you're working on. You really are leaving a legacy for others to follow in. So I'm very honored that you would make time to speak with me and our Origins audience today. So thank you so much.
Of course, thank you so much. It's been a pleasure.
Thank you for joining us on Origins with myself, Dr. Natasha Wilson. We hope that you will join us again. You can find us at www.originsconvo.com, as well as on Twitter and Instagram using the handle @originsconvo. Please join our Substack at originsconvo.substack.com, where we will post interviews and other interesting content for both free and paid subscribers. Thank you.